In this video, I will demonstrate how to perform linear regression in SPSS. For these purposes, we will use the following dataset. So in the dataset, we have a group of 77 students who completed a demographic questionnaire. So we have their age and gender. We have participants' personality traits measured by NEO 5-factor inventory. So then it's measured on a scale from 1 to 5. So 1 is strongly disagree, 5 is strongly agree. So the higher the number is, the more person possesses of that particular trait. So we have 5 traits. And we have the recording of the emotional intelligence using trait emotional intelligence scale. It's a scale of 30 questions and responses are recorded from 1 to 7. The absolute minimum score participants can obtain is 30 and maximum score of 210. So we just sum up the items of the scale to obtain the emotional intelligence score. The question we want to answer is, do big 5 personality traits predict trait emotional intelligence? To answer this question, we need to follow these steps. Test the assumptions, compute descriptive statistics, and compute inferential statistics. So here are our assumptions. So the outcome variable should be continuous. For us, outcome variable is on a scale, so it is continuous, and we already planned for it at the design stage of the study. So that one is checked. The outcome and predictor variables should be paired coming from the same person. Again, at the design stage of the study, we determined that. That's how we collected the data, so this one checked as well. No influential cases or outliers. There are two ways you can test it, using the normal exploration of the data. But actually, because we're doing a multiple regression, we're looking at how all 5 traits predict the emotional intelligence. We can use the Cook's distance, and we ask for this Cook's distance in SPSS. And this Cook's distance will indicate to us if there are any particularly influential cases that can affect the result of our outcome. So independence of observations. Again, we collect data and decide at the design stage of the study that our observations are independent. However, there is also a Durbin Watson test that we can ask for in SPSS just to check that the independence of observation assumption is met. The relationship between predictor and outcome variables should be linear. This is also tested in SPSS as part of the regression analysis, so you don't need to plot separate scatter plots for each combination of the variables. The residuals or arrows of the regression line are approximately normally distributed, so we can plot to see how the residuals are distributed, and that again can be done in SPSS as part of the regression analysis. We also need to meet the assumption of homoscedasticity, and this one is also tested in SPSS as part of the regression analysis. And finally, we want to check that there is no multi-colinearity, so i.e. that 2 independent variables or any 2 of the predictors are not too strongly correlated. And in SPSS, through regression analysis, we can ask for the variance inflation factor or for tolerance. I mean, once you ask for one, the other one comes up automatically, but you would only use one of those. So let's have a look at our data set. Here's our data set. So we have our neuroticism, extraversion, openness, agreeableness, conscientiousness, and our dependent variable in this task is trait emotional intelligence. So all the assumptions can be tested through the regression menu, so there is no additional steps that you need to take. We also can compute and ask for the correlation as part of the regression analysis, but the table is not presented in the most reader-friendly way. So in this case, I usually compute a correlation table first and then move to the regression because it's just easier to read that way. But let's have a look at what regression produces. To compute regression, you go to Analyze, Regression, Linear, and you allocate your dependent variable, which is in our case emotional intelligence, and you put all your predictor variables, or all your independent variables, into the independent variable box. So what additional things we need to specify in this menu in order to test all the assumptions? So when we'll go to statistics, the things we're interested in is colinearity diagnostics, and we also can look at part and partial correlation. Usually I would pick this one, and confidence intervals are commonly reported, so we can pick this one. And here is our Durbin Watson test that can test the independence of observations. So we'll check this one, and case-wise diagnostics to see if there are any cases. The outliers outside 3, so sometimes people suggest go for the outliers that are outside 2.2, but let's keep it as a default of what we have in here. So we put continue, and the next things we want to plot the data to look at how the errors are distributed. So we will put our predictor to the x-axis and the residuals onto the y-axis. And we also want to ask for the histogram. Histogram will show us the distribution of errors. Continue. Options. Nothing we need from here. Save. Okay. From here, we want to check the Cook's distance to see if there are any influential cases. So we select the Cook's distance and we press continue. So now our regression model is set, and we're checking for all the assumptions as part of this regression. So we press, let me just check that we selected everything we wanted. Yeah. Press OK. Okay, so this is our regression output. And what we see in here, firstly, the specification of the model. So we look at the conscientiousness, agreeableness, openness, extraversion, and neuroticism were entered as the predictor variables, and our dependent variable is emotional intelligence. So it basically just summarizes for us what's in the model. The next table is the model summary. And from here, there are a number of values you are interested in. So firstly, Durbin Watson test, that testing our assumption. So we have a value of 1.879. Oops. And if we look at our assumptions for Durbin Watson tests, the statistics for that test ranges from 0 to 4, and the value of 2 means there is no autocorrelation, so that the scores are independent. The values from 0 to 2 indicate positive autocorrelation, and values from 2 to 4 indicate negative autocorrelations. What you're looking for is the range of your values to be between 1.5 and 2.5. In this case, we'll consider it quite normal and quite good, and field suggests that values under 1 or more than 3 are a definite cause for concern. In our case, our value is close to 2, it's 1.8, so it falls between 1.5 and 2.5, and in this case we can proceed with the analysis because we meet the assumption. The other important values from this analysis, so we get our R, which is our correlation coefficient, which is kind of a combination correlation coefficient across all the predictors. We'll get our R squared, which is the proportion of variance our predictors explain in the outcome variable. So this is the proportion of variance that is explained by 5 personality traits in the trait emotional intelligence score, and they account for like 46% of the variance. However, most commonly used value for estimating how much variance predictor variables explained in an outcome variable is actually adjusted R squares. So this value takes into account the number of the predictors and usually provides a much more conservative value. But in this case, so our 46 dropped to 42.5. And this is the value you would report. You would say that 5 personality traits explained 42.5% of variance in trait emotional intelligence, and or you can include it as adjusted R squared equals 0.425. So report these statistics and report these statistics in order to kind of gain all the information you need from this analysis. So this one, Durbin Watson test, will be reported when you talk about how your data meets the assumption. R squared is how much variance the model as a whole explains in the dependent variable. Because regression belongs to general linear models, it also provides you the output for the ANOVA. And what ANOVA gives you is whether the model as the whole is significant. And this is pretty much the values you report. So you report your degrees of freedom for regression lines and for your residuals. Your F value and whether it's significant or not, to say overall the regression model was significant. But the most important table is this one, the table of coefficients. This is where you get your slopes and your intercepts. So the first one, constant, is your intercept, where the line starts. And your slopes are presented with the unstandardized betas and standardized beta coefficients. Because our independent variables, our personality traits, are recorded on a scale from 1 to 5, but the trait emotional intelligence is recorded on a scale from 30 to 210. So the scales are very different. So it's easier for us to understand how the line slopes when we look at the standardized beta coefficients. And these standardized beta coefficients, they have the t values to be able to see whether they're significant or not. So these three values are important and are usually reported in the regression table. So what we see in here is that neuroticism negatively affected trait emotional intelligence. So in a way, the increase in neuroticism results in 0.271 decrease in trait emotional intelligence, and it's significant. The next one is extraversion. Extraversion is also significant and it's positive. So more extroverted you are, the higher is your score on trait emotional intelligence. So with every score increase in extraversion, your trait emotional intelligence increases by 0.288 standard deviations. Then we have openness, and openness is not significant, so it didn't significantly predict the scores of trait and emotional intelligence. Agreeableness also not significant, but what we have significant is conscientiousness. And conscientiousness is the strongest predictor out of the three significant predictors. So the neuroticism negatively impacts, extraversion positively, but if you're high on a conscientiousness, you're also high on the trait emotional intelligence. So, and this is how you would interpret the regression lines. The next values we ask is confidence intervals. They're commonly reported along with standardized beta coefficients. And if the lower bound and the upper bound do not have zero between them, the result is significant. So we have no zero between these two values. We have no zero between these two values. We have a zero between these two because one is negative, another one is positive. We have a zero between these two because one is negative, another one is positive. And we have no zero between these two values. So basically, what the confidence intervals tell us that in 95% of the cases, that would be the slope of the line. So the slope of the line for here can range from -2 to minus 0.3. And because we're fitting the best regression fit line, and this is inferential statistics, so what it allows us is to infer from our sample how things are working in the population of interest. And in this case, 95% confidence interval tells us that our regression slope will land between these two values. So, for example, in a non-significant result, what it tells us that our regression slope potentially could be 0. And regression slope of 0 implies there is no relationship between the two values. Then what we also get is our zero-order correlation between our predictor variable and our dependent variable. So zero-order correlation in this case is simple Pearson correlation. So we can see that actually simple Pearson correlation between neuroticism and trait emotional intelligence was minus 0.513. So it was strong negative correlation. For extraversion, it was moderate positive correlation. For openness and agreeableness, the correlations were a bit weaker, but still positive. And for conscientiousness, the correlation coefficient was again moderate and positive. And what is interesting in here, that's when we see how variables fight for the variance inside the dependent variable. So the idea is, for the regression model, is we want to explain the most variation in trait emotional intelligence with the use of the least predictors. So in regression, the simpler model that explains the most variance is the preferred model. In statistics, simplicity is beautiful. If you can make it simple and most effective, that is the best model you can estimate. So in this case, what we see is as we put all variables together, that they start fighting for the variance starts getting separated into the partial and part correlations. So other variables start stealing these variances. And what we can see in here, as we starting excluding the confounding effects from the Pearson correlation. So let's say from neuroticism, we start excluding the effect of all other variables. So all the correlations between neuroticism and other variables in the model, like neuroticism and extraversion, neuroticism and openness, neuroticism and agreeableness, the correlation becomes weaker and weaker. And this is because the two variables, this is because all variables in the model correlate with each other. We hardly ever see, especially with the large samples, that there are absolutely no relationship between the variables. So the next part that we're interested in, and that is for testing the assumptions, is the collinearity statistics tolerance and VIF. So what those ones are, let's have a look. Did I include it in here? No, I did. Oh, there we go. So those values give us the results for multicollinearity. So variance inflator factor indicates whether a predictor has a strong relationship with the other predictor. As general rule, we want the variance inflation factor to be no more than 10. If we have variance inflation factor of more than 10, there is a likely problem for collinearity. The tolerance gives us exactly same information, but it ranges from 0 to 1. So the closer tolerance to 0, the stronger the relationship between a particular predictor and other predictors in a model. So what do you do if your tolerance or your variance inflation indices are high for that variable? You need to consider to remove that variable from the model. Basically, you have in the model two variables that are highly overlapping, and there is no need to use two highly overlapping variables. They're going to fight for the variance in the dependent variable, and you don't want that type of fighting. So what we see in our output is all these values are quite far away from 0. So we are quite happy. And variance inflation index is way away from 10. So these two provide exactly same information. If you're talking about the multicollinearity, you can pick to report either tolerance or variance inflation index, but you don't need to report both because they provide exactly same information. The next variable of or the next output of interest that we want is to look at the distribution of errors, the distribution of residuals, and in here we want to see if our variables are more or less normally distributed, quite a normal distribution of errors. So in this case we are happy, and this is the plot that allows us to examine the homoscedasticity. So let's have a look how it can look. So the assumptions of homoscedasticity is that variances in arrows is equal across different kind of values of the predictors. And what we want is we want to see plot like this, where all dots are scattered in the middle in a kind of somewhat circular fashion. When we don't meet an assumption, we can see heteroscedasticity, is where everything is clustered around the higher values of our independent variables. We may also observe a non-linear relationship in here, and if we observe that that's a problem, we can't rely on the results of the regression. Or we can also observe the heteroscedasticity that is not linear, so values are getting clustered in particular area. So when we look at our plot, we can see that they are in a way forming a circular fashion and scattered around. So in this case, our heteroscedasticity assumption is met. So, and this is how you read the results of the output. Just to recap, the most important values you need to report in relation to assumptions. In relation to assumptions, you're looking at this plot, you report homoscedasticity. Looking at this plot, you can conclude the distribution of errors, and if it is normal, your assumption is met. From this table, you're looking at multicollinearity, and you can report VIF, and this value needs to be below 10. from the model summary, you report Durbin Watson test for the independence of scores. And then another thing we wanted to look at is the Cook's distance, which is to see if there are any influential cases. The Cook's distance is saved in the data file. So if we look at it, here is the Cook's distance. And what we want, this value to be between 0 and 1. So Cook's distance gives the measure of the influence of a particular case on a model as the whole. Cases with the value greater than 1 are a cause of concern. Let's have a look what we have in our data. So sort descending from the largest, and we see that our very largest factor is 0.17, so quite far away from 1. And in this case, in this data set, we do not have any influential cases. So when you sort the variables, when you work with the large data sets, you can't just keep scrolling all the way down. If you have like, okay, here's 77 people, but if you have a data set of like 400 people, you can't be scrolling and paying attention to all these values. So you start looking at your data set in forms of the descriptive statistics or sorting the values as ascending or descending. Now, in this case, all our assumptions are met. So if we'll go to our assumptions, so we already determined we met these two. Cook's distance is okay, we satisfy these assumptions. Durbin Watson test is okay, we satisfy these assumptions. The relationship between predictor and outcome variable should be linear. We looked at how linearity could be gotten from the predicted and residual scores, and it was linear. The residual errors of regression line are approximately normally distributed. We saw on a histogram that the distribution was relatively normal, and homoscedasticity should be assumed. So we looked at the spread of values in the plot, and we saw that the spread is in a circular fashion with no values clustering in any one corner. And multi-colinearity, we look at the variance inflation and tolerance, and they were all within their range. So in this case, we say that all of the assumptions for regressions are satisfied. So when you report the results of the regression, the results of the analysis, the most important values to report are adjusted R-square to explain how much variance is accounted for by your predictors in the dependent variable. So in this case, you reported 42.5%. That the overall model you estimated is significant. So you report degrees of freedom for regression and for residuals. You report the F value and whether it's significant or not. And from this table, the important values is standardized beta coefficient, whether it is significant or not. And you can, in addition, report confidence intervals. So those are the three main tables for interpretation of results. And this is it.